Ray, just looking at the bearing capacity factors, we've got phi is greater than 0. It's got NC is NQ minus 1 over tan theta. Where I went wrong is I used that equation and then I tried to work out NQ and put that back into it rather than take the 2 plus pi.
Oh, right. Oh, I see. Yeah. Okay.
So spend a bit of time on that. That's quite a nasty calculation, that, using the NQ.
Oh, it's not. Yeah. That's why they've tried to give us all these tables and things to help us.
But I couldn't find that NQ on the table.
The NQ. Let me just find the piling map tutorial. Wrong one.
Is it not on figure 1?
Yeah, so NQ you read off
Table A1 and figure 1. There's a graph and a table.
So it's N gamma.
It's N gamma, not NQ though.
N gamma. So if you look at figure, I think it'll be figure 1 in your folder. So it's table A1, got a graph of N gamma against phi. And if you've got phi of, for example, 40 degrees, your N gamma is 109.
Okay, yeah, got it.
Yeah. So you just read it off the graph.
Do you think enough time to go over the trench support one today?
No, probably won't, because that's. I mean, of all the things that we do, that trench design is probably the easiest. You'll be able to work that out for yourself. I want to do some steelwork design simply because it's a little. I want to show people how to design a needling scheme. So I think most people are involved in fairly small little projects. Well, some of you might be in larger projects, but a lot of you are involved in smaller projects, and needling is one of the most common things we do in temporary works.
Ray, I have 3 clients waiting already, so you need to get onto the needling works.
Derek, I want to share your profits, my friend.
Don't worry, I'll let you in on a little secret. I'll let you in on a little bit of work that is coming your way soon. It has to do with the changing of plastic with windows, the plastic windows, installing plastic windows with the mass failure of the lintels and the buildings falling down around them. But that's the next argument. Totally.
So they changed the lintels in order to change the windows, and then they put
what happened? No. This has been going on for the last 10 years. Everybody is going through the saving the planet malarkey. So they have taken out the old windows and put in PVC windows. But what they've done is disturb the lintels. So what is happening now? We have mass failure of lintels. I have 3 properties around my area with massive cracks. One is falling down right now. They had to move out the family out of the property, and they have 2 more going right now. So with all this eco trending that the government is sending to make your building greener, with the boys coming in to rip out the windows, that is what is going to follow. So there's a lot of work. There's a lot of work coming our way. Let's put it that way.
I'll tell you what I've seen there. Are they bay windows? Just a single window?
No, there's a mixture. There's a mixture as long as you use PVC windows.
I'll tell you what I've seen is with a lot of older buildings, you may have had windows. See if I can draw it for you. This is something that the Victorians used to do a lot. You may have had a window set up like this, where you call mullions in beam, and your lintel, which could be basically went over the top of them like that.
Yeah, that's correct. Yeah.
But these mullions are structural.
Yep,
So
they are.
Again, if you replace that with a
PVC.
big plastic window that does that,
Ray, I think we need to go into a bit of business here, because I let's let you in on the scam.
That's the problem. People don't realise these stone mullions were structural.
Yes, they are. They are.
If you remove that mullion, then you will end up with a load of trouble with that lintel. It will fail.
Yep.
But often these lintels, they may have been made in 3 sections to make them easier to lift.
Yep.
Yeah, so that's quite common. Because otherwise you just end up with one massive, great big lump of stone, and you need about 20 men to lift it up.
Yep.
So put it into smaller sections so 2 men could lift it. Yeah, and people forget if you remove that, your lintel's knackered. Well, I've seen that a lot.
You did mention that we're going to talk about facade retention. Then way there might be a little bit of a session on that facade.
Okay. A few minutes at the end, we'll do a little bit on facade retention. I just got one question from somebody about related to cranes. Can I just share this with you very quickly? Let me just make sure I do this properly. So share screen. I think it might have been Amjad, I think. Who was asking about other machines, not just cranes, but things like you could get cherry pickers, newps, these sort of machines. Okay? Exactly the same principle, but just be aware of this. This machine, that outrigger load is about 2 tons, 20 kilonewtons. Can you see they put the foot straight onto the ground? Okay? And that foot is about 150 by 150. I know it's round, but if I call it square, it makes the maths easy. Okay, so let's work out the pressure. 20 kilonewtons divided by 0.15 by 0.15. Now check it on your calculator. I'm making pretty close to 900 kilonewtons a square metre. About 890 or something, isn't it? Yeah? You find me some sort of soil that will carry that sort of pressure. Unless you've got a concrete slab or granite, you're in trouble. So, I would always expect to put some piece of timber underneath it. Right, so let's put a bit of timber sleeper underneath it. So let me just work this out. So we've got, get my calculator. Really. Okay, so if I put a timber sleeper underneath it, 125 by 250, that direction, if I spread the load, I'm limited to 250. Go in this direction, in and out of my piece of paper, I've got 150 plus 250 plus 250, which is 650. So if I work out that, if I've got 20 kilonewtons divided by 0.65 divided by 0.25, look at the difference. Just by putting a little bit of timber underneath that machine, you've gone from a pressure of nearly 900 kilonewtons a square metre to a pressure to just over 100. I always worry when I see these sort of machines parked straight on the ground. I would always expect people to put something underneath them as a spreader. Would you agree? That is a massive load. Okay? That is absolutely huge.
Right. The point I'm making this, I think, point is just to make sure, like, the design brief won't normally covers this cherry picker, or like if you have like a piling mat. I think on site people are thinking, I think it's designed for the piling rig. Why can't you have cherry pick on the piling mat? It's a very basic common error is meant. I think made by the site operation team. So that's why I would like to everyone on this.
End up with such massive point loads. So you have to spread the load underneath these machines. And would you all agree that is a massive load? That is absolutely huge. A 90 tonne a square metre. Right, let's do a little bit of steel work. Takes us into sort of refurb. And so what we should hopefully we'll have a few minutes at the end to talk about facade retention. Now, I think the first thing to just make sure we're all happy with, how do we specify steel? Okay. If I wanted this particular section, okay, if I wanted to buy, another one of these, what information would I have to give the stockist in order to buy it? What information do we need to specify steel?
Size.
Good. Now, for example, this particular one is a 152 by 152 by 23 UC. Okay? What's the 152? Well, it's the height and the width. What's the 23? Kilograms per metre. A lot of people think you specify steel by thickness. No, you can't, because, well, this one's not quite so clear. What's that part there called? Flange. What's that bit there called? What's that bit there called?
Fillet.
The fillet or the root radius. The flange is a different thickness to the web. Generally, the flange will be thicker than the web. And as you come around the root radius, can you all see the thickness is not constant? So you can't specify the thickness because it's not a uniform thickness. So the other thing we can specify is the weight per linear metre. Okay? Now what does UC mean?
Universal column.
Universal column. So what that means is that dimension nearest damn it is the same as that dimension. You can then have something called a UB. What's a UB?
Universal beam.
Universal beam. PFC. What's PFC?
Parallel flange channel.
Parallel flange channel. You can then have CHS.
Circular hollow section.
RHS. Angular hollow. SHS. Square hollow section. Then you can have T's and plates. Right? UBP. Oh, now I've got you boys, haven't I?
That pile.
Universal bearing pile. Okay? They're basically UC sections that are made specifically thick so we can drive them into the ground as a foundation pile. And they're called UBPs. So, why is it 152 by 152? Why is it not 150 by 150?
Is it old money for that 16 or 6 inch?
In proper money, it's 6 inches. Okay. The next one up is 203, which is 8 inches. You then go to 254, which is 10 inch. The biggest one I think they do for universal beams, they definitely do a 914. I think there might even be a size bigger than that. I can't remember what it is. Okay. However, be careful. I have been told you can get metric equivalents. Okay. So you can get a 150 by 150. Okay. Now for these small sections, I'll be honest, I've never seen a metric equivalent, so I don't know if any of you guys have. You apparently can get metric equivalents. When the sections are small, the difference is almost nothing. When you start getting into big sections, the difference could be quite substantial. So something like a 914 universal beam, I presume the metric equivalent would be 900. That's quite a difference, isn't it? Yeah. Have any of you guys come across metric equivalents? I'll be honest, I've never seen them, but people have told me they exist. I've never seen them. Never seen them. All right. So apart from size and weight, what else do we need to specify? Grade. Right, we'll come back to grade in a second. Anything else? How long do you want? Length. Okay, how long do you want it? Okay. What about things like surface finish? Okay, you can specify different finishes. So you could get it galvanized, you could get it powder coated, you could get it delivered with intumescent paint on it. What's intumescent paint?
Fire
Fire protection. How does intumescent paint work?
Retardant stuff. Slows.
It's a
The way
vapor, doesn't it?
paint works is when it gets hot, it expands, it bubbles up, and it forms a protective layer for the metal. Because the metal itself won't burn. It's not like wood. Metal doesn't burn. What happens to metal? It melts. Okay? So what it does, it forms a barrier around it to stop the metal melting. Okay? And the other thing you can specify could be things like fabrication details. So maybe you want something to drill some holes in it for you, so you can put some bolts in. Okay? But let's have a look at this whole thing about grade. I'm hoping I'm sharing this screen properly with you. Can you see something that says steel work? Okay, great. Now, what do we mean by grade? Now, I'm going to take you back to when you was all about 14 or 15 years old, and you're in school doing a science lesson, probably physics. Now, I would imagine your teacher gave you a spring and some weight. Okay? Now, who remembers doing this? What you did was you put a load on the spring, and then you had to measure how much the spring moved. You put another load on it, measure it again, take the load off it, measure it again. Okay? Now, when you was 14, you had to plot a graph. Now, my daughter did this not long ago, so I can, I know what I'm talking about here. When you was 14, I bet your teacher made you plot load against extension. Okay? Because we're not 14 anymore, and we're engineers, let's call it stress and strain. And to start off with, your graph looked like that. And what it says is load is to extension. What do we call this behaviour?
Elastic range.
Elastic. So your piece of steel behaves in an elastic manner. So that means when you put the load on it, it extends. When you take the load off it, it goes back to its original length. Now, would you agree, at some point, gentlemen, when you put enough load onto that spring, what happens to the spring?
It deforms.
It permanently deforms. So I believe what happens is on a molecular level, the molecules sort of slide over each other, and then they can't go back to their original position. What do we call that point?
Elastic.
Elastic limit, or the. And when we're specifying the grade of steel level, we say 7 newtons a millimetre squared. Okay? Now, the way they derive that is the people that manufacture the steel, they will test 1,000 samples of steel, okay, until it yields. And they plot a graph of all the yield values. And what you not end up with is a graph that looks a bit like this. Okay? Who remembers this from school? Standard distributions, don't they? What it's based on, what the yield is based on, is what we call a 95% confidence limit. Okay? What that means is if they test 1,000 samples, at least 950 of them will have a yield more than 275. Okay? The average value, the mean, might be about 285 or something. Okay? Now, our piece of steel, our spring, has not physically failed yet. You can still put more load onto it. And your graph does something like this. What is this particular range here?
Plastic.
Plastic. So your steel behaves in a plastic manner. And eventually, you keep the load on, eventually the spring will just break. Okay? So this is a typical stress-strain curve for what we call mild steel, grade 275 steel. Okay? Now what happens if we got a higher grade of steel? Okay? We still have the same straight bit, okay? But can you see the plastic range becomes shorter? And the next grade up is probably grade 355 steel. Okay? You then go up even higher, an even higher grade of steel. Okay? You see this line is a constant. What's the gradient of this line? What's the gradient of that line? Sure, Young's modulus, isn't it? Young's modulus is simply your relationship between stress over strain, which is a constant for a material. And the next grade up, now I'm going to say 460. Some of you gents might be more familiar with 500. And the reason I use 460 is when I started on site, high yield deformed reinforcing bar, we used to call it, for example, T16, T20, okay? Who's old enough to remember when rebar had the letter T next to it? I'm sure some of you guys are, okay? And what that meant was it was manufactured to an old British standard, and I think the standard was it 446, okay, for reinforcing bar, and it required a minimum yield of 460 newtons a millimetre squared. Nowadays, how many of you are more familiar with rebar where they call it H16 or H20? You know, so maybe people like some of you who might be a bit younger than me, you might be familiar with H. Why has it gone from T to H? What's the difference? Europe. This is made to European standards, so this was made to British standards, which had a minimum yield of 460, to European standards. Does anyone know what the minimum yield for reinforcement should be? 500. Okay? Now what we're looking at here, gentlemen, is typical stress-strain curves for an increasing grade of steel. Now this is the important bit for temporary works. Okay? This bit here. In my opinion, for temporary works, this is the steel we should be using. Okay? And there's a number of good reasons for that. First of all, a lot of steel we use for temporary works is second-hand. Okay? So somebody's bought it, and they'll use it time after time after time after time. Unless you've got some sort of identification on it and you have the original certification, would you be able to tell what grade of steel this was? You can't sort of, I'll tell you what, you can't do this, fellas, and say, yes, that's definitely high yield steel. Yeah. I wish it was that easy. You can't do that. So unless you are 100% sure that you know what it is, it's mild steel. Because quite often people would have lost all the certificates for it. Okay. Number two, quite often we want to join bits of metal together. We could use bolts or we could weld. Now, if you're using mild steel, the welding procedures are relatively simple. Okay? So even somebody like me can weld it. I've got a welding set in my garage. I've got what's called a MIG welder. And if I wanted to weld something on, a piece of metal on top of that, okay? Or I do stick welding, what we call manual metal arc. I've got welding rods, okay? I run a current through the metal. The other end of the current is the welding rod. And I can deposit metal, molten metal along here, and I can weld the two bits of metal together. For mild steel, the welding procedures are simple. As you increase the grade of steel, the welding procedures become increasingly more complex. So for example, when you get to 355, you have to heat the rods. When you get up to 460 steel, you probably, depending on the thickness of the steel, you probably have to heat the parent metal and then control how it cools. What could be the problem if you allow it to cool to...
Brittle.
Yeah. Your weld start cracking, your stoops could get, it's called brittle, embitterment or something like that. Yeah. So you've got to be very careful how you start welding grade steels. And because the procedures are a lot more complex, it ends up being really expensive. And one last really, really useful bit. Can you see, as we increase the grade of steel, the plastic range becomes short, brittle. Okay? The big benefit of mild steel is if you overload it, it gives you lots of warning that you've overloaded it. What warning sign does mild steel give you that you've overloaded? Deflection. Okay? Because you've got a very long plastic range, a piece of mild steel will deflect very significantly before it breaks. So if you're on site, if you're in a cofferdam or you put up a facade retention scheme, that piece of steel is telling you that there's something wrong. Hopefully you've then got an emergency procedure and you get everyone out of there. The problem is, as you increase the grade of steel, yes, you can put more load on it, but because the metal is brittle, you load it, you overload it even a little bit, and it basically goes bang. Okay? It gives you very, very little warning that something goes wrong. You load it, you overload it slightly, and it fails catastrophically. So for me, gentlemen, if at all possible, try and use grade 275 steel for temporary welds. Okay? Do you think I've given you a convincing argument for that? Yeah? Now, in fairness, 355 steel, you do actually get a lot for your money. Can you see the difference in yield is about 30%? Okay. What do you think the difference in price is? Do you think 355 steel is 30% more expensive than 275 steel? No, it's probably about... Yeah, it's probably... The difference in price is probably only about 5%.
Yes.
very much. It's much the same.
You then go from 355 to 460, and the difference in price is next to nothing. You actually get good value for money buying higher grade steel, but for me, there is a risk and associated costs with welding, using second hand, and the whole fact that it's brittle. Okay, so there's swings and roundabouts. Now, why do these look like this? What's the benefit of that shape? Why do they make them look like this?
Economics.
Because when I put something into bending, like that, the top goes into compression, the bottom goes into tension. Where is your maximum tension and compression? Tension and compression.
Extreme fibers in top and bottom.
On the extremities. So if you did a distribution, okay, let's say you've got compression and tension, it will look something like that. So you've got maximum compression, maximum tension. What do we call the middle?
Neutral axis.
Okay, the neutral axis. So on the neutral axis, there is no stress. What we're trying to do is to put as much metal as far away from the neutral axis as we possibly can, because that's where we need it. There's no point in having a load of metal in the middle because it's not doing anything. So can you see, if you look at the shape, okay, they're trying to put as much metal up here and down here because that's where you need it. Okay? But that then gives us a bit of a problem, because when we put this into bending, what can happen is we start getting instability of the compression flange. Okay, so if I bend this and bend this and bend this, the compression flange becomes unstable and it will buckle. Okay? So the critical mode of failure for the beam is instability of the compression flange. Okay? And one other problem with this shape, if I put a big point load on top of it, okay, the web now acts as a strut, as a prop. And what do we know happens to sort of fairly slender props when we put a big compressive load on them? So you then have an issue with instability of the web. So if you put a big point load on it, I suppose one of two things can happen. Your web could fail something like that, or I suppose it could fail something like that. How do we get around this particular problem? Web stiffness. And of web stiffness. Okay? What we do is we put plates to support the web. Now here's a fundamental rule of temporary works. Okay? This comes from the British Standard. If you have points of load concentration in steelwork, you put web stiffness in unless you can prove by calculation you don't need them.
That's standard detailing.
So it's one of the clauses in BS 597. I can't remember the clause number, look it up yourself. But it says if you've got concentration and load. So what we mean is a beam sat on top of another beam. A beam sat on top of a column. A beam sat on top of a wall. Okay? You've got a high load concentration at the supports. You put web stiffeners in unless you can prove by calculation you don't need it. Now, has anyone ever had to design web stiffeners? They are a pain to do. Your design costs are do you know what? Sometimes it's cheaper just to put them in than to prove you don't need them. It's actually cheaper to put web stiffeners in than to calculation to prove you don't need them. Okay, so the fundamental rule is for temporary works, if we have load concentration, we put web stiffeners in unless we don't need them. Okay, is everyone happy with that particular concept? Okay, now be looking at a code of practice called BS449. Okay, who's old enough to remember British Standard 449? Okay, the old. Can you find 6? Okay, it'll be page RKF066, I think. And we're going to design one of the most common bits of temporary works that we have. We're going to design a little needling scheme. Okay? How many of you gents have been involved in a project where you've had to do something similar to this? And we need to support the wall until we get some sort of new supporting. We call it. Now, the theory behind it comes from the lintel code. What we look at is a triangle of loading applied to the top of that lintel. Because brickwork has an ability to arch. So if you form a fairly small hole in the wall, the brickwork will arch around that opening. Okay? And the way I do it is, let's say we want to put a new door or window in. Okay? We know that to the window, therefore we know the size of the lintel that needs to go above it. Does anyone know what's the minimum bearing that we have on a lintel, either side of your door? Or 150 mil. So if you go to building regulations, I think they recommend a minimum bearing of 150. Okay? So let's say a 2 metre window in. Our lintel has to be at least 2.3 metres long. Would you all agree with that? So you've got a minimum of 150 mil either side. Now, in order to put a 2.3 metre lintel into the wall, the hole we make has to be a bit more than 2.3 metres, isn't it? Yeah, that's fairly obvious. Yeah, you can't get a 2.3 metre lintel to fit into a 2.2 metre hole. Yeah? It doesn't fit. So what we do is we basically just knock out the bricks. I always take it as you just say they knock out the nearest brick either side of where your lintel is going to go. And a standard brick size is 9 inches with the mortar, so you could take it as 215. So what I do is take the size of the lintel and add 250 mil either side, and that's the size of the hole. And then what we do is we take a 45-degree triangle, and all the load in that 45-degree triangle is applied here. And then we have something called an interaction zone, which is 60 degrees. And you then have to use a bit of engineering judgment. Anything in here, in that 60-degree triangle, you also need to make a judgment on. So, for example, if I had a floor spanning and the joists of the floor sit in there at this sort of level, and I form a hole underneath it, does that floor affect the loading underneath it? Yeah. So can you see we've got these two triangles? So number one is your 45 degrees, so you take all the loading at 45 degrees, and then you have to use a bit of engineering judgment on that 60 degree. Okay? Now, a piece of advice here, if you had a steel beam here, so your floors span that way, okay, and your floor span that way, and then this beam span the wall, I think I'd put a prop directly underneath that steel beam. For a high point load, I would just take the load off the wall, because you'll get yourself in trouble trying to design your needles. So just get a big prop and prop the beam independently. Just take the load off the wall. Okay? Now, this is the example we are going to do. And this is based on a real project. So what we had is we need to form a new hole in the wall, here. We've got a slab. The span of this room is 5 meters. So this slab spans between this wall and this wall. Okay? The self weight of the floor is not slab, it's a wooden floor, 0.5 kilonewton a square meter. We're going to add some live loading up here, 1.5 kilonewtons a square meter. What I need to do is work out the reaction here. Okay? So it's the load, 1.5 plus a half, times the span over 2. Okay? So my reaction here is 5 kilonewtons per meter. Now, the length of my lintel is 3 meters for the new door. So the size of the hole I've got to make is 3 meters plus 215 on one side, 215 on the other side. So it's 3.43. This diagram, what we're seeing is that the base of that triangle is 3.43. Okay? Now, to make it easy, we're going to put some needles in here. Do you think we should use the same size needle? So if we had 3 or 4 needles, do you think we should use the same size? I think that makes it easier for your people on site, doesn't it? One of the problems I've often seen is designers design a needling scheme and they put 1 needle in the middle, the 2 either side will be a different size, the 2 on the outside will be another completely different size. What's going to happen on site when they start building this?
Mistake, that will make mistake.
Yeah, absolutely. Yeah, somehow they will get them the wrong way around.
Definitely.
Yeah?
I was involved in a project recently, and it really took the grace of God to me to make sure the builder made a mistake, but not as damn. But obviously, I could see how easy the builder could just do anything.
Absolutely, especially when you design them all the same size, but they're different weights. Yeah. So with UCs, with these 152s, the bottom weight is 23, the next weight is 30, the next weight I think is it 35 or 37? Yeah. And it's very easy because they're all the same size, we just get them in the wrong order. So if you make them all the same size and weight, you have made it idiot proof. Okay? Just make them all the same. So to make the maths easy, instead of this being a triangle, let's just take it as a rectangle and we'll design all the needles for the same load. Okay? So the height of my triangle is 1.715. Right? Now the brickwork is 330 thick and the approximate density of brickwork is about 19. It's about 18 or 19. Okay? So if I put density of 19, I've got 330 thick times a triangle 1.75 high times a density of 19. So I've got a reaction of 10.8 kilonewtons per meter. Okay? So that's the weight of the brickwork. I then add it to the reaction from the floor. So my total point load or line load is the reaction from the brickwork and the floor, which is 15.8 kilonewtons per meter. Now, I always recommend with needles, we put them at a maximum meter centers. Okay? If your brickwork is in not great condition, you have to put them closer together. Okay? But maximum metre centres. So I'll tell you what, whilst I've got this photograph up, look at this scheme here. I think this scheme has been put together by idiots. Why do I say that? Where's the load, gents?
8 panels.
So would you agree with me that one looks about the right place? These two, I think I'd want to see them a bit close together. That one's probably in the right place. What the hell is that one there contributing? What is that supporting? Yeah, you probably got 2 courses of bricks there. So what could you use instead of needles underneath the windowsills?
Strong boy or something like that.
Strong boys. How many of you gents have heard of something called a strong boy? Okay. I'd like to make it sound a clever piece of equipment. It isn't. What it is, it's a standard acro with a big plate on the end of it. Okay? And what you do is you cut a little bit of the mortar out and you poke it into the wall. Okay? They are designed to carry very, very small loads because if you look at it, it is a massive eccentric load. Okay? So what happens is you generate a huge moment. Does anyone, standard acro, you could probably put about 2 tons on it. When you put the strong boy plate on it, does anyone know what the capacity of the acro with a strong boy is?
About 250 kilos.
Give or take. If you said 300 kilos, you'd be right. You're not far off. So the way to look at it, gents, is if you need 1 acro to carry the load, you're going to need at least 6 of these. Yeah, maybe even 8. Okay, can you see the difference in the capacity? Okay? So I would not use them to support a big load, but underneath a windowsill, you could put a few of these in underneath the windows. Right? So if we're putting in our needles at metre spacing, my point load is going to be 1 metre times 15.8. So we then need to design the steel needle. Okay? Now, so there's my needle. I've got a point load of 15.8. If I use this particular steel for my needle, it has a self weight of 0.23 kilonewtons a metre run. And then I personally always allow for a block and tackle. The reason is, let's go back to here. Right. If we had to get a new steel up here, how would we do it?
Pulley system, block and tackle.
So the trick, gentlemen, is you should always put the new lintel down here before they start. Okay? You then build all the temporary works around that piece of steel. You put a block and tackle on it, so it's basically just a pulley system with a chain. You can put the chain onto the steel, and then they can fit up into position and slide it in. Okay? One of the funniest things I ever saw on a construction site was this. They built the temporary works first. It was in quite a small room. The steel beam then turned up on site. The steel beam was about 4 meters long. How do you get a 4 meter long steel through a 1 meter gap in your propping? I had to go and visit the site, and when I saw what they'd done, well, I promise I nearly wet myself laughing. As an adult, I think that's as near as I've come to wetting myself. Okay? Since I was about 3 years old. Okay? Fortunately, they hadn't started to demolish the wall yet, so I said, look, you've got to take your temporary works down, slide the steel in, and then put your temporary works back up. Okay? They simply hadn't thought through the sequence. Right? So I would always allow for a block and tackle, so we can work out some bending moments. I've got a point load in the middle, and if I block a tackle is at the same location as the point load, just to make the maths easy. Okay, I've got PL over 4 plus a bit of self-weighted bending. So I add up all the bending moments. I have 8.4 kilonewton meters in bending. Okay, can you all follow what I've done so far? Are you all happy with this? So this is pretty basic stuff. All right. What we now have to do is to design the steel beam using 449. And what we need to know about is something called effective length and restraints. All right, how many of you vaguely remember this? If I have a column section or a beam, okay, and it's a length L, and I put a load on it, it's going to deflect like that. So my effective length is basically going to be my length. Okay? So for this case, your effective length is simply length. Now what happens if we can build the ends into a wall? So we concrete them or brick them into a wall. Okay? So we've got full restraint. Okay? What happens now is it does something like that. Okay? How many of you gents remember all of this? So what we're looking at in terms of length is that distance there. Now, can anyone remember what's the effective length for something like this? 0.7. Yeah, I think it's is it 0.7? I think it's 0.7. Okay, so your effective length is 0.7. Okay, the other extremity is, for example, if you had a cantilever, and what happens there is it does something like that. And what we now have to do so what's the effective length for a cantilever?
2 times 0.
Okay. I'm hoping you're reasonably familiar with this. Okay, you're all hopefully reasonably familiar. Now, one of the clauses in BS 449 says, if we've got a steel beam and we support it U-head, can we argue that that is restrained in any way? Are we providing any restraints to the compression flange? No. So the rule there is it's 1.2 times your length plus double the thickness of the beam. Okay? So the effective length is 1.2 times the length of your beam plus double your depth. And then the beauty of BS 449 is you have to work out 2 ratios. Okay? The ratios are your effective length divided by your radius of gyration in the y direction, and the ratio of your depth, the overall depth of your section, divided by the thickness of your compression flange. Okay? So you need to get the section properties. Now, where do you get section properties from? Yeah, or you download them. How many of you guys have seen the tables of section property? Okay? Right. Whoever came up with those tables, okay, there is a special place in hell reserved for them. Okay? Those of you familiar with the table, have you noticed some of the units are in millimetres, some of them are in centimetres, some of them are millimetres to the 4th, some of them are centimetres cubed. Yeah? Honestly, it's the devil's own work, isn't it? Okay? Why didn't they make all the bloody units the same? So be careful, gents, when you're using those section properties, look out for the units. Yeah? I mean, who's made a mistake before using those section tables where you've read it as millimeters rather than centimeters or something? Yeah? It is an absolute pig, isn't it? Okay? Whoever invented those tables, they are in hell, aren't they?
Just imagine the hell without the tables, though.
Oh, yeah, how much worse could it be? All right, so what we need to do is work out the ratio of LE over RY. Now, this is where you've got to be a little bit careful. What we're doing, and let me see if I can find the film to demonstrate this for you. One of the very first design courses I ever did was for a contractor called Costains, and I did the course with their chief engineer, an old friend of mine called Peter Laws, and we were really struggling to explain this whole concept of radius of gyration and buckling. Okay, so what me and Peter did was, let me see if I can share this with you. Share this with you. Sharing, share screen. Right. Okay. If we've got a steel beam, something like that. Okay, so that's going to be my needle, piece of steel. I'm going to bend it in that, so I'm going to put a point load there. So I'm going to bend it in that plane. Which way will it buckle? It will buckle that way. Okay? Look at the demonstration. So what we did was we got one of these plastic sort of beams, and Peter, all he's doing is putting some batteries on it. So he's loading it that way. Look at the way it buckles. Look at the direction it's buckled. He's loading it that way, but it's buckled that way. Okay? Well, clever that, isn't it? Now, this is where we have to be clever again. Right. The difference between British standards and Euro codes. Right. British standards, BS 449. Okay? The major axis is called XX. The minor axis is called YY. The is called Z. Now, am I correct in saying Eurocodes, they've got these the other way round? What could possibly go wrong, fellas? Yeah? Somebody tell me, which way round is it in Eurocodes? I'll be honest, I can't remember. Which one's which in Eurocodes? What's the major axis in Eurocode?
Z.
So Z is the major axis. What's the minor axis?
Y.
Okay, so that's still the same. So that means your longitudinal axis is... So all they've done is swap X and Z round, have they? Right. So don't make a mistake here. ES449, major axis is X, minor axis is Y, longitudinal axis is Z. Okay? Don't make a mistake with the tables. Right, so let's go back to my calculation. So hopefully I'm sharing this again with you. Okay. Right. So I work out my LE over RY. Okay. So remember, gents, I am bending this steel in the major axis, the X axis, but it's most likely to buckle in the minor axis. axis. Like you said, that bit of, okay? That's why we use the radius in the minor axis. Okay? So you work out these two ratios. You've got L over R, D over T. And then you read the permissible stress, the safe working load off the table. Okay? So what we have, L over R is 73. Okay? So what you do is you come down to here, 70, 75, so we're halfway between those two numbers. D over T is 22.4. So you go along the top, so we're about halfway between those two numbers. So you come down there, you go across there, okay, so we're somewhere in the middle here. And if you work it out, it tells you the allowable stress is 158 newtons per millimetre squared. So what that is telling you is if you put a stress of more than 158 newtons a millimetre squared onto that compression flange, it's likely to buckle. Okay? And allowable stress in 449, we use the big letter P. Okay? So then we have to work out the actual stress. And I hope you all know stress is your moments, applied moments, divided by your section modulus, M over Z. And you use the section modulus in the major axis. Okay? So this is the bit, you know, a lot of engineers get confused by. So we're bending it in the major axis. Okay? So we use the section modulus for the major axis. But when we're looking at buckling, it's going to buckle in the minor axis. So we use the radius of gyration in the minor axis. Okay? Just give me a thumbs up that you all understand that. I'm hoping if you use Eurocodes, it's similar, is it? Now, I'll be honest, I've never used Eurocode, so I don't know. No, I've never had to. Right? So, we work out our actual stress, and it comes to 151 newtons a millimetre squared. My allowable is 158. That stress is less than that, so my beam won't buckle. All I then do is check the deflection. And for reasonable brickwork, I would keep the deflection, the maximum deflection, to less than 3 millimetres. If you allow the brickwork to deflect, or your steels to deflect more than 3 millimetres, what happens to the brickwork you're supporting? What could start happening to the brickwork? There is a good chance, because it starts moving, Ash, there's a good chance you're going to start putting cracks in it. Okay? So if you keep the deflection less than 3 mil, there's a pretty good chance it won't crack and you don't have to pay for a load of expensive repairs. Okay? And then you simply, exactly the same as we did yesterday, you work out your reaction and you design a prop to carry your reaction. That's all there is to it. So you'll all be good at working out the loads. The beauty of 449 is you only need to work out two ratios, L over R, D over T. Read it off the table to get your allowable stress. Work out your actual stress in the beam, which is just your moment divided by your section modulus. Make sure one number's smaller than the other number, and then just do a deflection check. Make sure it's less than about 3 mil. Easy. So, let's get you guys to do a quick 5-minute example. Okay? What I want you to have a quick go at, and I know we're going to a little bit short of time, but I think it's worth you doing this, because I think you guys do a lot of needling, so it's worth having a go. Can you find, so the tutorial is section, let's tell you which tutorial it is. Right. Can you find section 905? 905. I don't think we'll have time to do all of this, but I'll give you 10 minutes, and then we'll have a 10-minute session at the end. So have you all found this tutorial? Okay, section 905. This is based on a real job we got with Kears. It was for BT, British Telecoms, and we picked up a contract where they had a load of old exchanges, brick exchanges with a concrete roof on it, and had to all the equipment inside these exchanges. Okay? And the new machinery going in there, it wouldn't fit through the door. Okay? So there was about 200 of these, I think, all over the UK. There's about 60 of them all over the UK. And we had the contract to go around the whole of the UK and make these doors bigger so they could put this new equipment in there. And what the director wanted was a standard detail. He said, look, I want one design, and I want to take this design from one job to the next job to the next job. So we just pack it up, put it on a lorry, and take it to the next job. And we want to use the same equipment, 60 times. Okay? You've got 152 beams. Prove that you can make it work. Okay? And hint, I don't think you can put the needles at meter centres. The load is too big. Okay, so I think if you close up the spacing a little bit, see if you can make it work. Okay, so work out your loads, just see if you can make that steel beam work. What I'll try and do is I'll give you a clue as to what spacing to use.
I think the dimension that says approximately 7.3 by 6.3 internal dimensions by 7.
Yeah. So if you said it's about 8 meters wide, this building. Okay? So can you see up here? We've got it's 8 meters. So that slab is 8 meters long. The roof. Okay. So 4 meters of it goes on the wall you're supporting. 4 meters goes on the other. You'll have to have a bit of a guess at the self-weight of gravel. What would you say the self-weight of a gravel roof might be?
16.
16, 17, something like that? Yeah? Let me just check what I did in the example. I've taken a gravel as 18. Okay? Here's a little hint. Put your needles at 900 spacing.
Right, have you ever come across the this brick brace?
Yep, absolutely.
How does that work?
I have absolutely no idea. I have very, very reservations about it.
Yeah.
I've had a big argument with the bloke who invented it. He thinks that he is Einstein. About him. What brick brace is like 2 little plates, and the idea is you put it into one of your vertical joints, you wind up it's like a bolt on it, and the plate opens up. And the idea is it puts the brick into tension. Okay? Static theory. So you're trying to make it into an arch.
Mm-hmm.
Now, what does an arch need for it to work?
Buttressing, sorry.
Buttressing. The buttressing. Well, I can sort of see it working if you're putting a small hole in the middle of a wall, the brickwork either side of it. Suppose that doorway or window is on the corner. Where's your buttress? What are you pushing?
No, quite.
Yeah. So I've got, and the problem is the way the guy has sold it. He sold it as the answer to the maiden's prayers. Yeah, you can do absolutely anything you want with it.
Yes.
You can't.
Quite.
Yeah.
No, contractors don't do that way.
It's exactly the same as strong boys. The people who sell strong boys will claim you could build Hinkley Point Power Station if you had about 4 of those strong boys. Yeah, that's what they'll claim.
Yeah.
You can't. All of these bits of kit are, in my opinion, very, very limited usage. Very limited usage.
All right.
Hello?
Bushy here. Just related to that, I'll ask it in a slightly different way. If you put the bricks in the just above the opening into compression,
Yep.
right? Enough compression.
Yep.
Without the need to buttress either end of it, right? To carry what's the brickwork in the triangle above. It's just a very flat arch, isn't it?
Absolutely. So I'll tell you what it's like, Dushi. It's like you getting a load of bricks and trying to hold them. So imagine this is a load of bricks and you're trying to hold them like that. Okay? If you've got 2 or 3 bricks, you can do it. If you've got 20 bricks, what tends to happen is it does that, and your line of thrust for your arch, like I say, it's a very, very flat arch, goes beyond in effect, your arch goes into tension. And it fails. Arches do not work in tension. You have to maintain the compression. Yeah, but you're absolutely right. In effect, you end up with a very, very flat arch. So for me, it only works if you've got a very, very small opening and you've got sort of a decent buttress either side to hold the bricks in compression. Okay? If you want a big opening, what happens is the brickwork will just simply do that. It will just collapse in the middle. Very difficult to prove. Not easy to do. Okay. For me, the safest way of doing an opening is with a needling scheme. Okay? If doubts in your mind, just do a needling scheme.
You're a strong boy.
Yeah.
That's new to me. I didn't know that.
Well, let me show you a picture of a strong boy.
Well, I was just wondering, could you not brace the head of the strong boy?
You can do, absolutely. And that's one of the things, that is absolutely one of the things we do. But how often do I see your local builder do that? Never. Yeah, absolutely never. You can 100% brace it up with some scaffolding, but I never ever see your local builders do that. Let me show you what a strong boy looks like if I can find a picture of one. You've never seen them before. Here we go. I can share this with you. Share screen. Am I sharing this properly with you? Can you see? Yeah. So the prop, this is just a standard acro prop. The strong boy is this patented plate bit. And the idea is you basically hammer it or put it in the wall, and then you expect it to carry 1 million tons of load. Can you see the problem here? Because it's such an eccentric load, can you see that acro is already starting to buckle? Okay? So they are very, very limited usage. Very limited usage. I would only use them for small openings in thin walls. If you want to put a big hole in a fat wall, this is completely the wrong piece of equipment to use.
Because you end up needling it.
Absolutely, you end up having to needle it. So you end up with, I mean, this is the biggest needle scheme I ever designed. Where is it? This thing here. Great Northern Hotel in London. The wall was 675 mil thick, solid brickwork. The loads were so big. Is it-
Universal beams.
What, sorry?
They look more than universal beams.
These are very I can't remember the size of these now. I think they were three. I can't remember. They were about 300 and something deep beams, and I did it in threes because we had to manhandle everything down here. Okay? I could have done that with one massive beam, but we'd have never got it in there. There's no way we would have been able to carry it down there. So I had to make the beams smaller, so we had a chance of putting them into position. Access here was a nightmare. There was pretty much no access. We couldn't get any machinery down here at all.
What are the props sat on?
What
are the props actually sat on?
A 600 by metre wide or 900 wide concrete strip footing.
Is that something that you had to put in yourselves?
Absolutely. Okay. Because what we had, this is down in the basement. So the basement slab was only something like 125 thick or 150 thick. And I had a real concern if we put big point loads on it, we just break the slab. Okay. So what we did was we saw cut, put a trench in either side of the wall, basically filled it with concrete, and then built a propping system off that.
You have to brace the soldiers.
Yeah, for stability. Yeah. I would always do that just as good practice.
They brace from one side to the other, from one line to the other, or braced against the ground.
You'd certainly brace them left to right, as we're looking here.
What about the other direction?
In the other direction, what you then got to look at is how stable do you think the wall is likely to be. The problem with putting bracing the other way is the existing wall gets in the way when you want to put your bracing. Okay? So you could do it like this. Let me just draw it for you. So instead of bracing that way, you put individual towers either side to brace it. Okay, so if you're worried about stability of this wall, brace it in both orientations. And an easy way of doing it is just build towers either side. The other advantage then is you can put some platforms on here, some boards, and you've created a working platform for your people to stand on.
Hey, do you have a design example using those slim shores? I assume they look like the RMD slim shores. The last
That's
time I
all.
looked at it, they had the bits at the top, that let you expand. That's nearly one of the critical. You find the slim shores that carry a lot of the weight. When you extend those up, it's limiting. So
Absolutely, it's the extension of the jack. So for me, yes, you're quite right. It'll be the extension of the jack. So there'll be a table that says if you extend the jack a certain amount, this is the capacity of it. So whatever load you've got, on the drawings you'll have to put the jack can't be extended more than whatever 300 mil or 400 mil, whatever it says off the tables. Okay? But the actual capacity of the soldiers in compression is pretty good. If you can brace them up, the actual capacity is, I think it's about 120 kilonewtons or something like that.
I think they have two grades. I think so the light one is about 120.
You then but that is a massive set. That is a massive lump of metal. It's absolutely huge. One of the problems you'll have there is actually handling it. because you'll end up with manual handling problems because they're so heavy. You'll need machinery to move the stuff around. Okay, has anyone had a crack at that example? Let me just get the answer up for you. Okay. Close that now. So I can get the answer for you. I think you've got this in your course notes anyway. If I just find the answer for you. So let me just share this with you again. So share screen. Okay. So this is the example or the bit we saw earlier. Let's have a look at the answer you guys have been doing. Okay. So I think this is the example you guys have been having a go at. So that's by loading. So I've got self weight of the console, the live loading up on the roof. So I make my reaction. So if you do, so that 2's moved over. It's WL over 2. I make my reaction, give or take 44 kilonewtons of meter run. Okay. The size of the opening is if we do that 45-degree triangle. Okay. However, above here, we've got less brickwork. So we don't use the whole of that triangle. So all you do, just design for all the brickwork. So the height of the remaining work is, I think, is about 1.3 meters. Okay. So you work out your self weight of the brickwork. I said, have a go at your needles at 900 spacing. Okay, so these are your reactions. So you do your PL over 4 and WL squared upon 8. You then do your L over R, D over T, and my allowable moment was 158. My actual bending moment, stress, was 145. And then do a deflection check, and you know what? It was near as damn it 3 millimeters. Yeah? 3.1 millimeters. Well, I'm going to say that's good enough. Okay? And you've got the answer in your folder anyway. Okay. Just for the last couple of minutes, do you want to have a quick word about facade retention? Facade, there we go, something like this. How many of you gents have been involved in a facade retention scheme at all? So something like this. This is the first facade retention I ever designed. It's in South Wales. Can I recommend a book to you? Who's seen this before? It's a Syria book. It's called The Retention of Masonry Facades. I was involved in writing this. There are 3 of my case studies in there. Okay, what's the number? Is it C579?
579. Okay. I think that's
C579. Okay. What we designed for is obviously the wind loading, and then to maintain stability, every point where you connect the to the facade, we design for 2.5% of the vertical load above that point acting horizontally. Okay, so you've got two principal loads. One is your wind loading. Secondly is 2.5% of the vertical load acting horizontally. And you simply design it like we did for shuttering. You look at overturning. Okay? So would you agree a facade is basically just a big hoarding or a big shutter? Yeah. It's just a straight wall and we want to stop it falling over. Okay? So you have to look at overturning. And what's going to stop it falling over? Damage. Okay? So one very common way of doing facade retention is we just put big concrete blocks at the bottom of it. Okay? So you work out your overturning, and then AO, you have to work out if you've got sufficient weight in your Kentledge to stop it overturning. Okay? Also check for sliding. Okay? Thing could slide. But here's a little trick for you. See if I can find a picture of it. Here we go. Right. This is one I designed in Cardiff. Look at the difference in the Kentledge. Can you see on the outside leg, we've got a massive lump of concrete. On the inside leg, I've got a fairly small lump of concrete. Why is that? Well, let's look at how this is actually designed. I think this is one of the case studies in that book, actually. Okay, there's your facade, there's your facade retention. Let's just put another brace in there. If the wind is blowing from that direction, okay, the whole thing wants to overturn. So what I'm relying on is the weight of that Kentledge block there. Okay? If the wind is blowing from the other direction, a little trick you can do is you prop off the underside of the facade. So if you've got things like doors and windows, you put a prop to the underside of the facade, and then you can use the self-weight of your facade to help prevent overturning. That's why you end up with a much smaller Kentledge block on the inside than the outside, because we're utilising the self-weight of the facade. Okay? It's got a useful little... AO saves an awful lot of concrete on site. Okay? Now, on this particular site, I discovered a problem. I went to this site. I was in Cardiff. Now, can you see those Kentledge blocks? They were building them in situ. So they made some shutters, and they basically filled them with concrete. Now, the foreman doing this job, doing the concrete, he said, underneath, we've got some quite nice paving. So what was the foreman doing to protect the paving when we poured concrete on top of it? What did the foreman do?
Some DPM.
He put some polythene down. Okay? So on top of the pavement, you got some polythene, put the shutter up, and then filled the shutter full of concrete. Okay? What are we relying on to stop that sliding? What happens if we put polythene? What happens to the coefficient of friction when we put polythene in?
It's reduced by 0.2.
Do not put polythene underneath a Kentledge block if you're going to run friction. Now, luckily, I think they'd only done one or two of these, so I made them demolish it, take the polythene away, and do it again. And I said, look, if you're worried about the paving, get a pickaxe, get the paving up, put the paving round the back of the site somewhere, and then relay it when you finish the job afterwards. And if you're worried about the paving, just lift it and put it somewhere for safekeeping. Relay it afterwards. You do not put polythene underneath your Kentledge blocks. So we designed for wind plus 2.5% of the vertical load acting horizontally.
Ray, the wind calculation there is the same as the hoarding calculation.
Pretty much, yeah. Obviously, your height and stuff will be slightly different. You could design the winter Eurocode if you wanted to. Yeah. Absolutely.
Appropriate for the hoarding, and you have your time scale and all that coming in, which which you end up then with more reasonable figures.
You may well do, absolutely. Because when you think about it, your facade is going to be substantially bigger, so you're going to have a lot more wind. It's going to be there for quite a period of time, I would have thought. So if you want to, get your wind load down a bit, you might be better off designing it to Eurocode.
More likely to be in Oxford than at the top of the cliff.
I don't think there's many listed buildings on the top of cliffs, unless there's some sort of lighthouse or something.
Right, Ray, set design for the wind plus 2.5% of this facade self-weight.
Yes. So 2.5% acts horizontally. So at each one of these points, so if you're connecting to the facade there, is 2.5% of that acting horizontally.
Cumulative or?
Well, just the weight above it. Okay? So if you've got 2 meters of facade there, it's 2 meters times the density, 2.5%. At this point here, you might have 3 meters of facade. So 2.5%, 3 meters. But that's only for each of your connections. Okay, so at each connection point, you have to design it for 2.5% of the vertical load acting horizontally.
Is there some sort of spreader plate on the inside face where it's connected through the facade? What's on the other side?
The way I connect them to the facades is I utilise the window openings. So the detail I would use is, let's say that's your facade, that's your window. Okay, so there's your brickwork. Okay. What I would do is run. You can do it top and bottom. I would sandwich it either side of the window opening. So if that's your wall, you're sort of grabbing hold of it like that either side.
If there's a lot of window openings in that facade, is that a line of weakness there?
It can be. So what you then have to do is you need to start. Can you see this photograph? You might then have to start bracing up your window openings. Am I sharing this? Can you see the timber bracing we put in these window openings? They'll be quite large timbers. You're probably looking at sort of 225 by 75 timbers just to brace up your window openings. But
Frequently, you need to put points into the wall. The main sort of frames.
And you're breaking up, Ashley. You've got a really bad line there.
Is that any better? No?
Go on, carry on.
No, I was just saying, is there any sort of guidance on the frequency that you need to fix it back to the facade?
It depends on the quality of your brickwork. What you have to try and prove is that your brickwork spans between where you're picking it up. So wherever you're grabbing hold of the brickwork, you have to prove the brickwork can span. So you might get it to span vertically, or you might look at it expanding horizontally, depending on how you're going to pick it up.
Ray, just another question just there on the timber framing on the oaks. In the pinning exercises, like it's something we always do is we always frame out the window openings. Is there a cake? Maybe sometimes you don't have to.
Absolutely. If you think your brickwork is stable and you've got sufficient, because what you'd worry about there is lateral movement of your building. If you think you've got sufficient lateral support from buttresses either side, you don't need to worry about it. Yeah? You'd only worry about it if you're, let me give you one example if I can find it. I'm not sure if it's in this presentation. It was in central London, where we virtually demolished everything. And I haven't got it in this presentation. What we had was you imagine a house, and what they wanted was just the front panel of brickwork to remain. So we had to demolish everything underneath it, take the roof off, all the floors off. So literally that panel of brickwork had to be suspended in fresh air. Okay? And it could collapse like that. It could collapse like that. Or it maybe starts doing something like that. So then we had to provide a complete scheme around it to stop it failing that way, or start doing something like that. Because there's literally absolutely nothing around it to provide any sort of restraint. It was literally just a panel of brickwork suspended in fresh air. It would have saved a fortune if they'd let us knock it down and just rebuild it. You could have knocked it down brick by brick, you could have numbered every single brick, and you could have rebuilt it exactly with the bricks exactly in the same place they came from.
Who's the PD on that?
The
principal designer then?
This was, I think it's fair to say this was before CDM. This was about 1994 or 5. Yeah. All I had was a very, very rich client and English heritage. Okay? And English heritage insisted that we do this. And the client was prepared to throw money at it. Oh, fair enough. Throw some of it in my direction. And I shared one last one with you. This is the only time it's ever happened in my whole working life. When I worked for Kears, we picked up a job after a collapse. So in the book, you've got the full case study of this. A sheikh bought 4 terraced houses near Harrods, in central London. Okay? Obviously, he liked shopping, so he thought, well, I'll buy 4 houses near Harrods, as you do. And he got some dodgy builders in. They started to do a fairly big demolition job. 3 of the 4 houses collapsed. Okay? And they collapsed inwards rather than outwards. The sheikh threw the engineer and the builder, they just threw him off the job. His representatives came to see Kears, and basically the sheikh gave Kears a blank check. Okay? The director came to see me, and he gave me a design brief. Okay? And the design brief had 2 words on it. That was my design brief. Okay? It's the only time in my career I've basically been given a blank check. Okay? My design brief was sorted. Okay? And after the collapse, they got some scaffolders in to put some scaffolding up to stop the rest of it collapsing. For me, the big issue here was our contract is to rebuild this. How the hell do you rebuild with all of that scaffolding in the way? Yeah, you've got to get walls up, you've got to put doors in, you've got to put your plumbing in, you've got to get a roof on it. How the hell do you do that with all that in the way? So the first thing I had to work out was we got to create some space on this site. So progressively, we had to remove the scaffolding and replace it with these sort of towers. Okay? The only reason to do this was to create space, working space on site. Okay? Once we got the towers in, we could then start, rebuilding it properly. But, honestly, the director came to see me, and he basically had a blank check, and that was my design brief, sorted. Okay? I still have that design brief. I have kept it as a souvenir. I promise you, fellas, that sort of thing only happens once in your entire working life. Where, don't expect a blank check every job you do. Okay? It will only happen once. If
Check,
you're lucky.
blank check might mean money. Because
Yeah.
there's going to be the money reward there.
Yeah, it's whatever it costs.
Plenty sleepless nights.
Yeah, just throw money at it. Just throw money at it. So the full description is in that book. Okay, so have a look at it. It's all in here. Right, gents, we've gone on a little bit longer than I hope. I hope you've found it useful. Anyone got any last questions on anything we've covered? Have you all got something out of the last couple of days? Have you all found it? Have you all found it useful?
Very great experience, Ray. Thanks a million. I tell you, I thought I learned a lot out of it, a lot more than I had planned to, and there were some obvious shocks in there as well that I'll be a smarter engineer after it.
Well, that's really nice to hear from somebody with your experience, Peter. Thank you very much for saying that. That's spot on. Okay. Hopefully, I've demystified the dark art of temporary works design a little bit for you. Okay. For me, the key with temporary works designs is keep your calculations as simple as possible. Okay? Temporary works design is not about clever calculations. Temporary works design is about clever buildability. Okay? If you can design it as WO squared upon 8 and PL over 4, brilliant. Okay? You've got to think through the methodology. You've got to produce schemes that people on site can build. And the calculations is neither here or there. I promise you, you very, very rarely need to use 3D finite element analysis for temporary works designs. You need a cigarette packet and a pencil. Okay? Somebody's asking about fees. What was that about? Derek's asking about fees. Yeah, charge plenty of fees, Derek.
Ray, you remember when I started this course, I said to you, I want to start guessing. But there's a lot of estimation in this and a lot of engineering judgment.
Yeah, Derek, think of a number and then put about numbers on the end of it.
All right.
There you go. There's your fee.
That's all I needed to know.
Right, gents.
Yes, Ray, just one last point. I learned a lot there, and I think I'm coming from a building design and assessment of bridges side. It's given me quite a lot of confidence, but I'm not sure about the facades. I'll have to leave that to another day.
Leave
that does.
Yeah, leave that to the people that do it for a living. You stick to bridges, I'll stick to facades.
Thanks very much. Thanks.
No problems.
Right. Do you just one last thing? Do you run any further courses than this, or any carry on from this course?
No, but what I would recommend you do, hang on, just bear with me a second. There is a truly superb book you can go out and buy. Okay? It's called Temporary Works, Principles of Design and Construction. It's written by myself and my old friend Peter Pallett. This is the second edition. Okay? This is one, my friend.
I told you I want to go into temporary works.
Yeah, there you go.
I've studied the book before coming to the course. I've studied.
Brilliant. Now, somebody else has got it. I'll tell you. Well done. Thank you.
I've really read a lot of it.
Yeah. I mean, all I'm waiting for is my nomination for the Nobel Prize for Literature for this. Okay? I think it's going to come in the post any day. Okay? As well. Fantastic. Okay? I think every book you buy, I think I'll get about 50p. So if you all buy a copy of it, I might have enough for a pint of beer.
How much is it? Because if I'm not going to earn a fee on it, then I won't.
Yeah, it's not cheap. I think it's about 120, 130 pounds, something like that.
Wait for my first commission.
Yeah, Dushy, worth every penny, my friend.
Oh, no, thanks.
Yeah, it's worth every penny, my friend.
Keep me out of jail, it will be.
Yeah, there you go. Yeah. All right, gents. Hope you've enjoyed the last couple of days. It's been really good talking to you. Best for the future. I think they send you a feedback form at some point. They email you what do they call them, survey monkeys or something like that. So please fill it in, because I do take notice of what people's. Okay.
Brilliant.
So all the best.
Thank you.
Take care, gents.
Really appreciate it.
Right, really good. Cheers, mate. Bye.
Thank you so much.
Thanks,
Thanks, Ryan.
Take